Hello everyone. I will now begin the 8th video on pitch geometry. In the previous 7 videos on pitch motion, we examined front-wheel drive, rear-wheel drive, all-wheel drive, and braking, and in a recent video, we analyzed the dive of front outboard brakes. Rear-wheel braking has a power transmission path similar to front-wheel drive, and front-wheel braking has a power transmission path similar to rear-wheel drive. In this video, we will examine the rise during pitch motion when braking force is applied to the rear wheels equipped with outboard brakes. Unless otherwise noted, everything discussed in this video applies to cases where only the rear wheels are braked without front wheel braking, and the braking device is an outboard brake. In this video, both driving acceleration and braking deceleration are referred to as acceleration, and we will distinguish between the two by the sign of the acceleration. If the acceleration is positive, it is driving; if it is negative, it is braking; and if it is zero, it is constant speed driving or a stationary state. I will treat driving force and braking force in the same way as acceleration. Driving has a positive value, and braking has a negative value. I will now introduce the content of this video. In this video, I will explain how to analyze pitch geometry when braking forces are applied to a rear-wheel braking vehicle. I will explain the direction of forces acting through the links and the springs, and then explain the direction of the vertical component of force when these link and spring forces act simultaneously. Subsequently, I will explain how to analyze pitch motion and vehicle attitude using mathematical methods. I will explain how to derive the force-moment equilibrium equations when braking forces are applied to the pitch geometry, as well as how to determine the conditions for zero rise and zero pitch angle. Finally, I will explain the effective location of virtual reaction point, depending on which forces acting on the springs and links vary, and accordingly the rise and pitch angles are determined. I have a quiz for you. In a rear-wheel braking vehicle, which statement is correct when the virtual reaction point is located between the rise zero line and the pitch angle zero line? First, in absolute values, the link force is smaller than the spring force. Second, in absolute values, the link force and the spring force are equal. Third, the rear ride height becomes larger than in the static state. Fourth, the front ride height becomes larger than in the static state. Fifth, the rear ride height is smaller than the front ride height. Sixth, the rear ride height is larger than the front ride height. Please select the one correct answer from these 6. Regarding the sign and direction of the vertical dynamic loads on the links and springs, I will explain using the rear wheel braking force, shown in this figure, as an example. In this figure, delta WZR represents spring force, and delta FZR represents link force due to rear wheel braking. When the virtual reaction point exists between the road surface and the rise zero line, both of these forces are vertically upward and act as tensile forces on the springs and links. The rise zero line will be explained later. For ease of understanding, I will define the tensile force as positive. If each of these two forces has a positive value, it is tension, and if it has a negative value, it is compression. For example, if spring force delta WZR is positive, it is tension, and if delta WZR is negative, it is compression. In the case of rear wheel braking, if the virtual reaction point is below the road surface, delta FZR is negative, so it acts as a compressive force on the link, and delta WZR is positive, so it acts as a tensile force on the spring. If the virtual reaction point is above the rise zero line, delta FZR is positive, so it acts as a tensile force on the link, and delta WZR is negative, so it acts as a compressive force on the spring. This will be explained with a figure later. The amount of vertical dynamic load transmitted to the rear wheel during braking can be expressed by equation 1. Additionally, since the sum of the vertical dynamic load of the spring and the vertical dynamic load of the link is equal to the amount of vertical dynamic load transmitted, this can be expressed by equation 2. Meanwhile, if we denote the ratio of the vertical dynamic load of the link to the total vertical dynamic load as eta r, this can be expressed as equation 3. Therefore, the vertical dynamic load acting on the link can be expressed as equation 4. From equations 2 and 4, the vertical dynamic load of the spring, delta WZR, can be expressed as equation 5. The amount and direction of the vertical dynamic load acting on the spring, delta WZR, are determined according to equation 2, once the link force of the suspension with the brake wheel, delta FZR, is determined. Since it is difficult to understand the direction of the force using expressions such as a vertical dynamic load acting on the spring and a vertical dynamic load acting on the link, we will refer to the negative force as the compressive force and the positive force as the tension force. Compression force is a force that increases ground reaction force, and tension force is a force that decreases ground reaction force. In springs and links, the representative symbol for compression is indicated by a vertical downward arrow, and the representative symbol for tension is indicated by a vertical upward arrow. Although the rear wheel braking force, FXR, acting horizontally on the road surface, acts in the negative x-axis direction, to use the same equation for acceleration and braking, it will be used without a minus sign, in the same way as acceleration, AX. This will also be explained later. Let's analyze the vertical component of the force on the links and springs during rear wheel braking. To analyze pitch motion, the most important factor is analyzing the forces acting on the suspension links where the braking wheel is located. For example, when braking force is applied to the rear wheels, but not to the front wheels, to analyze the pitch motion, we must first calculate the forces acting on the rear suspension links where the braking force is applied, delta FZR. The value of the vertical dynamic load transfer remains constant once the acceleration, AX, is fixed and can be expressed as equation 1. Since the springs and suspension links are the only paths through which the load is transferred, all forces are transmitted through these two paths. In the rear suspension with the braking wheel, the vertical dynamic load transfer is equal to the sum of the force on the rear suspension links, delta FZR, and the rear spring force, delta WZR. Therefore, it can be expressed as equation 2. In equation 2, AX represents the braking deceleration and has a negative value. Therefore, in equation 2, delta WZR and FZR both have vertically upward directions of action and act as forces that tension the spring and link. Since no braking force acts on the front suspension, the amount of vertical dynamic load transmitted through the front suspension links is 0. Therefore, the amount of vertical dynamic load transmitted by the front suspension is equal to the force compressing the spring, delta WZF, and can be expressed by equation 6. Since the acceleration, AX, has a negative value, the vertical dynamic load acting on the front spring minus delta WZF has a negative value and acts vertically downward to compress the front spring. Once the amount of the braking deceleration is determined, the amount of the vertical dynamic load transmitted is determined, and the ground reaction force at the front wheels increases by the amount of the vertical dynamic load transmitted, while the ground reaction force at the rear wheels decreases by the amount of the vertical dynamic load transmitted. If acceleration, AX, is constant, the decrease in rear ground reaction force must also have a constant value. Therefore, the sum of the reduction in rear spring force and the reduction in rear suspension link force must be equal in amount to the reduction in rear ground reaction force and opposite in direction. Consequently, since the vertical dynamic load transfer is constant in absolute values in the rear suspension, if the force acting on the rear links increases, the force acting on the rear spring decreases, and conversely, if the force acting on the rear links decreases, the force acting on the rear spring increases. However, in the front suspension, since no vertical force acts on the front suspension links, the force acting on the front suspension links is zero, and force acts only on the front spring. Let's examine the conditions for zero rise and zero pitch angle during rear wheel braking. Since the vertical dynamic load transfer, the increase in front ground reaction force and the decrease in rear ground reaction force are determined by the laws of physics. Assuming acceleration ax is constant, they hold constant values regardless of the geometry of the suspension links. The condition for zero rise during braking is that the rear spring displacement becomes zero. To make the rear spring displacement zero, one must make the vertical dynamic load acting on the rear spring delta WZR 0. By changing the geometry of the rear suspension links, the position of the rear virtual reaction point, SR, can be altered, thereby changing the amount of the resultant force acting on the rear suspension links. Let's examine the relationship between the link and spring forces based on the location of the virtual reaction point. The method for determining the pitch angle zero line and the rise zero line in the figure will be explained later. The pitch angle zero line can be expressed as equation 7, and when the front spring stiffness and the rear spring stiffness are equal, equation 7 can be expressed as equation 8. Figure 1 represents the case where the virtual reaction point, SR, lies in the region below the horizontal line connecting the front tire road contact center, point A, and the rear tire road contact center, point B. This area is indicated in light yellow. In this case, based on absolute values, the vertical force, tensile the spring, is greater than the resultant vertical force, compressing the links. In this case, eta R has a negative value, which is less than 0. Figure 2 represents the case where the virtual reaction point, SR, lies on the horizontal line, connecting the front tire road contact center, point A, and the rear tire road contact center, point B. In this case, the resultant vertical force of the rear links is 0, and only a vertical force, tensile the rear spring, exists. In this case, the value of eta R is 0. Figure 3 represents the case where the virtual reaction point, SR, lies in the region between line AB and line BG and is shown in light green. Here, point G is the point in the side view where a longitudinal horizontal line, having the same height as the center of gravity, CG, intersects the vertical line passing through the front tire's road contact center, point A. In this case, a vertical force tensile the rear spring and a vertical force tensile the rear suspension links are generated, both acting vertically upward. In this case, eta R is greater than 0 and less than 1. Most commercially available vehicles have a virtual reaction point in region 3. Figure 4 represents the case where the virtual reaction point, SR, lies on line BG. In this case, since the vertical resultant force of the rear links is equal in amount and opposite in direction to the vertical dynamic load transfer, the force acting on the rear spring becomes 0, and the force acting on the rear links supports the entire vertical dynamic load of the vehicle. Therefore, the brake rise is 0. In this case, the value of eta R is 1. Let's examine the relationship between link and spring forces based on the location of the remaining virtual reaction points. Figure 5 illustrates the case where the virtual reaction point SR exists between the rise 0 line, BG, and the pitch angle 0 line, BS, and is shown in light red. In the figure, Point S is the point where a longitudinal horizontal line parallel to the ground, passing through point U, which is at twice the height of the center of gravity, CG, intersects the vertical line passing through the front tire contact point, A. When the rear virtual reaction point exists in this region, the force tensile the rear links acts vertically upward, and the force compressing the rear spring acts vertically downward. In absolute values, the link force is greater than the spring force. In this case, the value of eta I is greater than 1 and less than 2. If a virtual reaction point exists in this region, the rear ride height decreases. However, the rear ride height remains higher than the front ride height, so the vehicle stance is lower at the front and higher at the rear. Figure 6 represents the case where the virtual reaction point SR lies on the pitch angle 0 line BS. In this case, the vertical resultant force tensile the rear links is twice the vertical dynamic load transfer, and the force compressing the rear spring is equal to the vertical dynamic load transfer. Since this force is equal to the force compressing the front spring, the same displacement occurs in the front and rear springs. Consequently, the pitch angle becomes 0, and the front ride height and rear ride height decrease by the same amount. In this case, the value of eta R is 2. Figure 7 represents the case where the virtual reaction point SR is in the region above the pitch angle 0 line BS. The reduction in rear ride height is greater than the reduction in front ride height, and the vehicle stance is higher at the front and lower at the rear. A force greater than the vertical dynamic load transfer compresses the spring, and a force more than twice the vertical dynamic load transfer tensions the links. In this case, the value of eta I is greater than 2. Let's analyze all the information explained above at once. This figure simultaneously illustrates the vertical force of the spring and the resultant vertical force of the links acting within the regions of the 7 virtual reaction points described earlier. As explained, when a vehicle brakes with a constant acceleration AX, the vertical dynamic load transfer of a rear-wheel braking vehicle, derived from Newton's second law, is represented by equation C. It has a constant value that does not vary, depending on the type of suspension and braking system. Therefore, when the vertical force acting on the spring and the resultant vertical force of the links are added together, the value represented by equation C must be the same in any case. Equation C represents the resultant vertical force acting on the spring and links, not the ground reaction force. By using eta R, the ratio of the resultant vertical force of the suspension links to the vertical dynamic load transfer, the spring force and the resultant vertical force of the links for the 7 virtual reaction points can be easily analyzed. Point 1 indicates that if the virtual reaction point exists below the road surface, the value of eta R is negative, implying that the force tensile the spring is greater than the force compressing the link. Number 2 indicates that if the virtual reaction point is on the road surface, the value of eta R is 0, meaning only the force tensile the spring acts and the force acting on the links is 0. Number 3 indicates that if the virtual reaction point is between the road surface and the rise 0 line, the value of eta R is greater than 0 and less than 1, meaning both the vertical force tensing the spring and the vertical resultant force tensing the links are vertically upward. Number 4 indicates that if the virtual reaction point is on the rise 0 line, the value of eta R is 1, meaning there is no vertical force acting on the spring and only the vertical resultant force tensile the links acts. In this case, the rise becomes 0. Number 5 indicates that if the virtual reaction point is between the rise 0 line and the pitch angle 0 line, the value of eta R is greater than 1 and less than 2, meaning the vertical force compressing the spring acts downward and the vertical resultant force tensile the links is vertically upward. Number 6 indicates that if the virtual reaction point lies on the pitch angle 0 line, the value of eta R is 2, and in absolute values, the vertical resultant force, tensile the links, acts twice as large as the vertical force, compressing the spring. In this case, since the same compressive force acts in the same direction on the front and rear springs, the pitch angle becomes 0. Number 7 indicates that if the virtual reaction point lies in the region above the pitch angle 0 line, the value of eta r is greater than 2, and in absolute values, the vertical resultant force, tensile the links, is more than twice as large as the vertical force, compressing the spring. In this region, the rear ride height decrease is greater than the front ride height decrease. Let's analyze the vertical dynamic loads acting on the suspension links during rear wheel braking. The link forces for pitch motion during rear wheel braking are similar to the link forces for pitch motion during front wheel acceleration. Forces acting on the links do not occur in suspensions without drive or brake wheels. They occur only in suspensions with drive or brake wheels. This simple fact is very important in the analysis of pitch motion. We have previously analyzed the vertical component of the force acting on the suspension links during accelerating front wheel as explained in the previous video, E0088, Pitch Geometry Part 2. This figure represents the case where the virtual reaction point is located in the region between the road surface and the rise 0 line. Since all forces shown here are dynamic loads, they are all 0 at constant speed or at a static state. When the rear wheel braking force, Fxr, is applied, the resultant force acting on the rear suspension links, delta Fzr, can be expressed as equation 9 using the vertical dynamic load acting on the rear suspension upper link, F1z, and the vertical dynamic load acting on the suspension lower link, F2z, and is indicated by the green arrow in the figure. The suspension link vertical dynamic load, delta Fzr, acts vertically upward and is a force that tensions the links, thereby reducing the ground reaction force. Minus delta Fzr represents the ground reaction force reduced due to the suspension link vertical dynamic load, delta Fzr. The suspension link vertical dynamic load, delta Fzr, is the vertical dynamic load transmitted through the link out of the total vertical dynamic load transmitted by equation 2. Next, let's look at the vertical dynamic load transmitted through the spring. Let's analyze the vertical dynamic load acting on the springs. First, let's examine the load transfer through the springs in the case of a rear suspension with brake wheels. In a suspension with brake wheels, the transfer paths can be divided into two. The first is the load transfer through the suspension links explained earlier, and the second is the load transfer through the springs explained here. In the case of a suspension with brake wheels, the sum of these two load transfers represents the total vertical dynamic load transfer of the vehicle. In this figure, we exclude load transfer through the suspension links and consider only load transfer through the springs. The amount of the load transfer through the springs depends on the location of the center of gravity, CG, and the virtual reaction point, SR. This will be explained in detail later. In most vehicles currently on the market, the vertical dynamic load transferred through the springs, delta WZR, acts in a direction that lifts the rear of the vehicle and tensions the rear springs. As a result, the rear ride height increases by delta R. Here, the displacement delta R has a positive value during a bump and a negative value during a rebound. Therefore, the rear ground reaction force minus delta WZR has a negative value and acts vertically downward. The vertical dynamic load, delta WZR, is the amount of vertical dynamic load transferred through the rear spring when the braking force, Fxr, is applied. As with the front wheel drive case, analyzed in the previous video, the ground reaction force minus delta WZR. Here is the ground reaction force generated solely through the spring, without passing through the suspension links, due to the action of the vertical dynamic load transfer, and it has a value of 0 in a static state. If the rear ground reaction force minus delta WZR for the vertical dynamic load acting on the spring is negative, it means that the total vertical load is reduced due to load transfer. If it is positive, it means that the total vertical load is increased due to load transfer. In the example shown in this figure, load transfer that tensions the spring occurs, resulting in a negative rear ground reaction force minus delta WZR, which indicates that the total rear vertical load of the vehicle is reduced accordingly. Let us analyze the vertical force components of the suspension links and the springs that we have analyzed so far. We will analyze the pitch motion of the vehicle when a rear braking force, Fxr, is applied and acceleration, Ax, is generated. When the vehicle is braking with acceleration, Ax, the total vertical dynamic load of the vehicle, that is, the load transfer from the rear to the front, can be calculated using Newton's second law, the height of the center of gravity, Cg, and the wheelbase L regardless of the suspension links or springs. The total vertical dynamic load transfer of the vehicle has a constant value corresponding to the braking force, Fxr, once it is determined. When vertical dynamic load is generated by rear braking, the vertical load on the front wheels increases by the amount of the vertical dynamic load, and the vertical load acting on the rear wheels decreases by the amount of the vertical dynamic load. These vertical dynamic loads represent the amount of load transferred from the rear to the front. Here, the important point is that in a rear suspension with a brake wheel, vertical dynamic load transfer occurs through both the spring and the link, whereas in a front suspension without a brake wheel, it occurs only through the spring. In this figure, delta WZR indicates that the vertical dynamic load acting through the spring acts vertically upward, causing tension in the spring, and delta FZR similarly indicates that the vertical dynamic load acting through the links acts vertically upward, causing tension in the links. As previously discussed, in a vehicle with suspension geometry, like the example in this figure, when a braking force is applied to the rear wheels, the vertical component of the force acting on the links of the rear suspension upper and lower arms acts vertically upward, and the vertical component of the force acting on the spring also acts vertically upward. Therefore, in this case, the vertical dynamic load acting on the rear wheels is positive, and it can be seen that the direction of the force is vertically upward, causing tension in the spring and the links. The ground reaction force for the total vertical dynamic load transfer is equal to the sum of the load transfer through the springs, delta WZR, and the load transfer through the suspension links, delta FZR. At the rear wheels, the vertical load is reduced by the amount of these vertical dynamic load transfers. Meanwhile, at the front wheels, which do not generate braking force, the vertical dynamic load is transferred to the ground as a force compressing the springs, so the vertical load at the front wheels increases. Since there is no load transfer through the suspension links, at the front wheels, the total load transfer from the rear to the front acts through only the front springs. This amount is equal to the total vertical dynamic load of the vehicle, calculated by Newton's second law, and acts as a force compressing the springs. In the previous video, E0001, Vehicle Dynamics Load Transfer, we studied the forces generated in an accelerating vehicle. Among these contents, we will review the load transfer for a vehicle subjected to acceleration Ax. All forces shown in the figure and equations, Fxf, Fzf, Fxr, and Fzr, represent the combined force of the left and right wheels. From the equilibrium of forces acting horizontally on the vehicle, equation 10 can be derived, and from the equilibrium of forces acting vertically, equation 11 can be derived. Additionally, equation 12 can be obtained from the moment equilibrium of all forces generated during acceleration around the vehicle's center of gravity, CG. From these three equations, the vertical force, FZF, acting on the front wheels during acceleration can be calculated as equation 13, and the vertical force, FZR, acting on the rear wheels can be calculated as equation 14. The first term, on the right-hand side of equation 13, represents the load acting on the front wheels at static state or constant speed, and the second term represents the load resulting from the decrease in weight of the front wheels during acceleration. Similarly, the first term on the right-hand side of equation 14 represents the load acting on the rear wheels at static state or constant speed, and the second term represents the load resulting from the increased weight of the rear wheels during acceleration. During braking, the acceleration AX has a negative value, and consequently, FXF and FX also have negative values. Thus, the direction of these forces is reversed, as indicated by the red arrow. If the acceleration and forces acting in the longitudinal direction are defined in this way, equations 10, 11, and 12 can be applied equally to acceleration and braking. The braking forces indicated by the red arrows, FXF and FXR, are negative. By using the results of the analysis of the forces acting on the rear wheel drive solid axle suspension links, which were examined in the previous video, E0081, pitch geometry part 1, rear wheel drive, we can easily analyze the forces acting on the links during rear wheel braking. For an efficient explanation, we will not consider the static vertical load acting during static state or constant speed, but will only consider the vertical dynamic load generated as a reaction to acceleration, delta FZR. All forces shown in the upper figure are forces generated by the rear wheel drive force, FXR, and all forces shown in the lower figure are forces generated by the rear wheel braking force, FXR. First, equation 15 can be derived from the equilibrium of the horizontal components of all forces acting on the rear suspension links during rear wheel drive in the upper figure. Equation 15 expresses that the driving force, FXR, must be in equilibrium with the resultant force of the horizontal component of the force, F1, acting on the upper arm, and the horizontal component of the force, F2, acting on the lower arm. Next, equation 16 can be derived from the equilibrium regarding the vertical components of all forces acting on the rear suspension links. Equation 16 expresses that the vertical component of the force, F1, acting on the upper arm, and the vertical component of the force, F2, acting on the lower arm, which are generated as reactions to the driving force, FXR, must be in equilibrium with the ground reaction force, delta FZR, for the vertical dynamic load on the rear suspension links. As mentioned, delta FZR does not include static loads and is the ground reaction force for the vertical dynamic load transfer on the links generated by the driving force, FXR. Next, equation 17 can be obtained from the moment equilibrium at point Q, where the center line of the lower arm intersects the straight line passing through the center of the rear wheel and perpendicular to the ground in the side view. The first term on the left side of equation 17 represents the moment generated by the driving force about point Q, and the second term represents the moment generated by the horizontal component of the upper arm about point Q. Solving equation 17 for the F1 yields equation 18 for the force acting on the upper arm, F1. Equation 18 expresses the force acting on the upper arm, F1, as a function of the driving force, Fx. Substituting F1 from equation 18 into equation 15 and solving for F2 yields equation 19. Equation 19 expresses the force acting on the lower arm, F2, as a function of the driving force, Fxr. Since the inputs for driving and braking are opposite, by reversing the signs of equations 15, 16, and 17, which represent the force and moment derived from rear-wheel drive, we can obtain equations 20, 21, and 22, which represent the force and moment generated by rear-wheel outboard braking. It is important to note here that, as explained earlier, the braking force Fxr is inherently negative, so its sign must not be changed. Solving equation 22 for F1 yields equation 23, which represents the force, F1, acting on the upper arm. Equation 23 expresses the force, F1, acting on the upper arm, as a function of the braking force, Fxr. Substituting F1 from equation 23 into equation 20 and solving for F2 yields equation 24. Equation 24 expresses the force, F2, acting on the lower arm, as a function of the braking force, Fxr. Let us continue to examine the concept of the equivalent trailing arm. As explained in the previous video, E0081, Pitch Geometry Part 1, Rear Solid Axle, all suspension links, including wishbone suspension links, can be replaced with an equivalent trailing arm using a virtual reaction point at any given moment during pitch motion. For rear wheel braking as well, the rear suspension links can be replaced with an equivalent trailing arm using a virtual reaction point. By substituting equation 23, which represents the force, F1, acting on the upper arm, and equation 24, which represents the force, F2, acting on the lower arm, into equation 21, and rearranging for delta Fzr, we obtain equation 25. Meanwhile, from the geometric arrangement of the rear suspension arms, the tangent value of the upper arm's mounting angle, with respect to the horizontal plane, θ1, can be calculated as in equation 26, and the tangent value of the lower arm's mounting angle, with respect to the horizontal plane, θ2, can be calculated as in equation 27. By substituting the derived equations 26 and 27 into equation 25, equation 28 can be obtained. From equation 28, it is shown that the ratio of the vertical dynamic load, delta Fzr, to the braking force, Fxr, is equal to the ratio of the vertical component, E, to the horizontal component, D, of the straight line connecting the rear tire contact center, B, and the virtual reaction point of the rear suspension, SR. Since the braking force, Fxr, is negative in equation 28, the ground reaction force, minus delta Fzr, generated through the link is negative, and it reduces the rear wheel ground reaction force. This fact indicates that in rear wheel braking, the upper and lower arms can be replaced by a single trailing arm that has the same virtual reaction point and is rigidly connected to a solid axle. As shown in equation 28, the vertical dynamic load, delta Fzr, is the ground reaction force for the resultant force of the vertical components of the forces acting on all links when the braking force, Fxr, acts on the rear wheel. As shown in the figure, during braking, if the virtual reaction point, SR, is ahead of the rear wheel and above the ground, the vertical dynamic load, minus delta Fzr, acts in a direction that reduces the entire ground reaction force Fzr at rear wheel. This time, we will examine the link force and spring force when rear wheel braking force acts and determine their relationship with the total vertical dynamic load transfer. The figure on the left shows the total rear wheel vertical reaction force, Fzr, the vertical dynamic load transfer, the rear spring force, delta Wzr, and the force of the rear links, delta Fzr. Here, Wsr represents the static vertical load acting on the rear wheel. G represents the acceleration due to gravity, and Ax represents the longitudinal acceleration. Delta WZR represents the vertical dynamic load that tensions the rear spring during braking. Here, delta WZR is the rear spring force converted into a force acting along a line passing through the rear wheel center and perpendicular to the road surface. Delta FZR represents the vertical dynamic load that compresses the rear suspension links during braking. FZR represents the total vertical load on the rear wheel. The total vertical force, FZR, acting on the rear wheel can be expressed as equation 29 by adding the static vertical load, WSR, and the total vertical dynamic load. The second term on the right side of equation 29 represents the vertical dynamic load transferred to the rear wheels. The reason the sign of the vertical dynamic load in equation 29 is positive is that the acceleration, AX, is negative, meaning that when the braking force, FXR, is applied, the vertical load, FZR, of the rear wheel decreases by the amount of the vertical dynamic load. In a rear suspension with a braking wheel, the ground reaction force, reduced by the vertical dynamic load transfer amount, can be expressed as equation 2A, which is the sum of the force, tensile the spring, delta WZR, and the force, tensile the links, delta FZR. Meanwhile, the rear wheel braking force, FXR, can be expressed as equation 30 using the force on the links, delta FZR, derived from equation 28 above. Remember that FXR is negative in braking. What we intend to determine is the relationship between the rear wheel braking force, the dynamic force, and the vertical dynamic load acting on the rear wheel spring, delta WZR. Then we calculate the displacement of the spring, and from this, calculate the rise and pitch angles. For a rear wheel braking vehicle, let's calculate the rear spring displacement relative to the rear wheel center. To do this, it is necessary to determine the relationship between the previously mentioned rear braking force, FXR, the vertical dynamic load, and the vertical dynamic load acting on the front spring, delta WZR. By calculating the moment with respect to the virtual reaction point, SR, we obtain equation 31. In this equation, the reason the sign of the last term is negative is that the braking force, FXR, is negative and generates a positive moment with respect to the virtual reaction point, SR. By simplifying equation 31 with respect to delta WZR, we obtain equation 32. Remember that in equation 32, the acceleration, AX, and the braking force, FXR, are negative. Meanwhile, the force acting perpendicularly to the rear wheel center, delta WZR, can be expressed as equation 33 using the rear suspension wheel rate and the spring vertical displacement relative to the rear wheel center. In equation 33, KR represents the rear wheel rate and delta R represents the rear spring displacement measured vertically at the wheel center, which is not a value measured along the actual spring axis. The first term of equation 33 represents the vertical dynamic load of the entire vehicle when the acceleration is AX, and the second term represents the vertical component of the force acting on the rear suspension links. Since no braking force acts on the front wheels, the force FXRED represents the force acting on the suspension links of the entire vehicle. From equation 33, it can be seen that the vertical dynamic load acting on the rear spring, delta WZR, is the difference between the vertical dynamic load transfer amount and the link force. Furthermore, from equation 33, it can be seen that if the vertical dynamic load of the entire vehicle is greater than the force acting on the links in absolute values, the spring force, KR delta R, is positive and acts in the direction of decreasing the rear vertical load. Delta R has a positive value at the bump and a negative value at the rebound. Let us continue to determine the condition for the rise to become zero. when braking force is applied to the rear wheels of the vehicle if no vertical dynamic load is applied to the rear suspension springs, the rise becomes 0. Furthermore, by calculating the spring displacement of the front and rear wheels relative to a line passing vertically through the wheel centers, we can determine the condition that makes the pitch angle 0 when braking force is applied to the rear outboard brakes. The rear spring displacement relative to the line passing vertically through the rear wheel centers was calculated using equation 33, and the front spring displacement relative to the line passing vertically through the front wheel centers can also be calculated from equation 35 using the previously calculated vertical dynamic load of the front spring, delta WZF. Here, delta WZF is the front spring force, converted into a force acting along a line passing through the front wheel centers and perpendicular to the road surface. In equation 35, Kf represents the front wheel rate and delta F represents the front spring displacement measured along the vertical line passing through the front wheel centers. First, let's examine the conditions under which the rise becomes 0 in a rear wheel braking vehicle. From equation 33, we can obtain the geometric conditions of the suspension where the rise becomes 0. For the rise to be 0, the force acting on the front spring must be 0, so equation 36 must be satisfied. Therefore, from equation 33, we can obtain equation 37. Since the braking force Fx can be expressed by equation 34, substituting Fxr from equation 34 into equation 37 and rearranging yields equation 38. For equation 38 to hold, the expression inside the parentheses must be 0, so we can obtain equation 39, which represents the conditions for the rise to be 0. Next, let's examine what geometry is required to make the rise 0. Based on the conditions expressed by equation 39 derived earlier, the geometry required to make the rise 0 can be represented as shown in the figure here. Point G is the point where a horizontal line passing through the center of gravity, CG, and parallel to the ground, intersects a vertical line passing through the front tire road contact point A. The pitch geometry is analyzed based on the bicycle model. The forces acting on the left and right wheels combine into a single force at the center longitudinal section of the vehicle. It is assumed that the center of gravity of the vehicle is located at the center longitudinal section of the vehicle. The green inclined line is a straight line connecting the rear tire road contact point B and point G. If a virtual reaction point, SR, exists on the inclined line between point B and point G, then according to the property of triangle similarity, the ratio of H to L always has the same value as the ratio of E to D, thus satisfying equation 39. Therefore, if the virtual reaction point, SR of the front suspension, exists anywhere on the green straight line shown here, this vehicle does not experience rise during braking. The absence of rise does not mean that the pitch angle is 0. Let us examine the relationship between rise and pitch angle. Let's examine the relationship between rise and pitch angles and suspension geometry using this figure. First, let's look at the relationship between rise and pitch angles when braking force is applied and the rise becomes 0. A rise of 0 means that the vertical spring displacement relative to the rear wheel center is 0, implying that the rear ride height has not changed. However, as indicated by the orange line in the figure, even though the vertical spring displacement relative to the rear wheel center is 0, the front wheel displacement is not 0, and the front ride height has decreased. To make the pitch angle 0, the rear ride height must be reduced to the level of the front, lowering it to the level indicated by the black line. To lower the rear ride height to the front level, the virtual reaction point, SR, must be raised. We will examine the reason for raising the virtual reaction point, SR, from two perspectives. First, the forces acting through the springs, and second, the forces acting through the suspension links. Let us examine, in terms of absolute values, how the forces transmitted through the springs and links change depending on the position of the virtual reaction point. If the virtual reaction point, SR, is raised, the amount of the vertical dynamic load through the spring, delta WZR, decreases in absolute values, while the amount of the vertical dynamic load through the suspension links, delta FZR, increases. Conversely, if the virtual reaction point is lowered, the amount of the vertical dynamic load through the spring, delta WZR, increases, while the amount of the vertical dynamic load through the suspension links, delta FZR, decreases. We will examine the physical implications of this through equations and figures. In this figure, the vertical axis represents the vertical height E of the virtual reaction point, and the horizontal axis represents the horizontal length D of the virtual reaction point. The origin of the coordinate axis is the center of contact center B between the braking tire and the road surface. In this coordinate system, if we rewrite equation 39, which represents rise 0, in terms of the independent variable, D, and the dependent variable, E, it can be expressed as equation 40. Equation 40 is the equation for a straight line passing through the origin B with a slope of h divided by L. Therefore, this equation can be represented by the green straight line in the figure. In the yellow region of the figure, the pitch geometry can be expressed using inequality notation as equation 41. In equation 41, as the height of the virtual reaction point, SR, EL, increases, the absolute value of the force on the suspension links with the brake wheel, delta FZR, increases. Since the total vertical dynamic load of the vehicle is constant if the acceleration, AX, is the same, the absolute value of the spring force, delta WZR, should decrease. In the yellow region, the spring force, delta WZR, and the force on the suspension links, delta FZR, act in the same direction. Next, let's examine the pitch geometry in the region above the green straight line. If there is a virtual reaction point in the area above the green line, the pitch geometry can be represented using an inequality expression, as in equation 42. In equation 42, as the height EH of the virtual reaction point, SR, increases, the amount of the force, FZR, on the suspension links with the brake wheel increases in absolute values, exceeding the amount of the total vertical dynamic load of the vehicle. In this case, since the total vertical dynamic load of the vehicle is constant, the direction of the spring force, delta WZR, is reversed, and as the virtual reaction point rises, the force tensile the link increases, and the force compressing the spring increases. In the region above the green line, the spring force, delta WZR, and the force of the suspension links, delta FZR, act in different directions. For this reason, if the virtual reaction point is located in the area above the green line, a compressive force acts on the spring, reducing the rear ride height to be smaller than in the steady state. Conversely, if the virtual reaction point is located below the green line, a tensile force acts on the spring, increasing the rear ride height to be larger than in the steady state. Meanwhile, the total vertical dynamic load transfer of the vehicle calculated using Newton's second law represents the load transfer from the rear wheels to the front wheels and is independent of the location of the virtual reaction point, SR. The role of the virtual reaction point is to determine the ratio of load transfer through the springs to load transfer through the suspension links. Once this ratio is determined, the rise and pitch angles are determined. Let's summarize the relationship between link force, spring force, and ride height. To calculate the rise and pitch angles, the first step is to calculate the force, delta FZR, which is generated in the rear suspension link where the brake wheel is located. Once delta FZR is known, the spring force and displacement can be determined from equation 2, and the ride height and pitch angle can be calculated. When the suspension geometry is determined, the magnitude and direction of the resultant force of the links, delta FZR, are determined. Let's examine how delta FZR changes depending on the suspension geometry. Equation 30, derived earlier, expresses the braking force, Fxr, as a function of link force, delta FZR. By rearranging equation 30 for the vertical dynamic load, delta FZR, we obtain equation 43. In equation 43, since the braking force, Fxr, is negative, the vertical dynamic load acting on the link, delta FZR, is positive. As shown in equation 43, the absolute value of the link force, delta FZR, increases as the ratio of E to D increases. From equation 2, if the braking deceleration, AX, is constant, the vertical dynamic load transfer is constant. Therefore, if the force acting on the suspension links increases in absolute terms, the force acting on the spring decreases, and the rear ride height increases less. If the virtual reaction point becomes higher, and is located in the region above the rise zero line, the vertical dynamic load acting on the spring changes from tension to compression, and the rear ride height decreases compared to the steady state. We will determine the conditions under which the pitch angle becomes zero by analyzing the forces generated on the springs and links, which vary depending on the suspension geometry. For the sake of convenience, we will assume that the front and rear suspension wheel rates are the same. Cases where these wheel rates differ will be explained later as we derive the formulas. In the rear suspension geometry of a typical commercially available vehicle, it has virtual reaction point SR below the rise zero line. In this case, when rear braking force is applied, the force acting on the links acts vertically upward to tension the links, and the force acting on the springs also acts vertically upward to tension the springs. The sum of these two forces represents the total vertical dynamic load transfer. Meanwhile, zero rise means that the rear spring displacement is zero, implying that the rear ride height has not changed. However, as indicated by the orange line in the figure, even though the rear spring displacement is zero, the front spring displacement is not zero, and the front ride height has decreased. To make the pitch angle zero, the rear ride height must be reduced to the front level, lowered to the level of the line indicated in black. To lower the rear ride height to the front level, the virtual reaction point, SR, must be raised. Raising the virtual reaction point, SR, increases the amount of dynamic load transferred vertically upward through the rear suspension links, delta FZR. Conversely, the amount of vertical dynamic load transferred through the springs, delta WZR, decreases by the same amount as delta FZR increases. To be more precise, in absolute terms, the vertical dynamic load compressing the springs, delta WZR, decreases by the same amount as the vertical dynamic load compressing the links, delta FZR. If the height, E, of the virtual reaction point, SR, lies on the straight line connecting points B and G, no vertical dynamic load acts on the springs, and all vertical dynamic load transfer occurs through the suspension links. Since no vertical dynamic load acts on the spring, the rear ride height does not change, and the rise becomes zero. However, since the rear ride height is still higher than the front ride height, the pitch angle is not zero. In the case of rear wheel braking, if the height E of the virtual reaction point SR lies above the line connecting points B and G, the force acting through the rear spring acts as a compressive force. Consequently, the rear ride height decreases, while the front ride height remains unchanged. As the virtual reaction point SR increases, the force attempting to compress the spring increases, and the rear ride height decreases. As the force attempting to compress the spring increases, the link force attempting to tension the rear suspension links also increases. By utilizing this fact, we can find the location of the virtual reaction point that reduces the rear ride height to 0 pitch angle. Keeping this in mind, let's examine the pitch angle. Let's calculate the pitch angle during rear wheel braking. By determining the wheel displacement of the front and rear wheels, we can calculate the pitch angle phi-p when braking force is applied. The rear spring displacement was previously calculated using equation 33, and the front spring displacement could also be calculated from equation 35 using the previously determined vertical dynamic load of the front spring, delta WZF. In equation 35, Kf represents the front wheel rate and delta F represents the front spring displacement measured along the vertical line passing through the rear wheel center. When the pitch angle phi-p is small, an approximation can be used in which the tangent phi-p is equal to phi-p. Here, the unit of phi-p is in radians. After rearranging equation 33 for the rear spring displacement, delta R, and rearranging equation 35 for the front spring displacement, delta F, and substituting these two displacement values into the second equation of equation 44, the pitch angle phi-p, when braking force is applied, can be obtained as shown in the third equation of equation 44. Here, the spring displacement has a positive value at the bump and a negative value at the rebound. Rearranging equation 44, the pitch angle phi-p can be expressed as equation 45. As expected, the pitch angle phi-p expressed by equation 45 indicates that it can be expressed as a function of acceleration, mass, front and rear wheel rates, and the geometry of the rear suspension link. Let us examine the meaning of equation 45 in detail. Let's determine the condition for the pitch angle to become 0. In equation 45, which represents the pitch angle phi-p, derived earlier, if the rear wheel braking force is applied and the braking deceleration AX is not 0, the condition for the pitch angle phi-p to become 0 is that the sum of the terms inside the parentheses in equation 45 becomes 0. Therefore, if we derive the condition for a 0 pitch angle from equation 45, it can be expressed as equation 46. Equation 46 can be rearranged for E over d to obtain equation 47. The first term on the right side of equation 47 represents the anti-rise condition of equation 39, derived earlier. As previously explained, in general suspension geometry, the condition for 0 rise is not the same as the condition for 0 pitch angle. From equation 47, if the front suspension wheel rate has a significantly larger value compared to the rear suspension wheel rate, the second term of equation 47 can be ignored, so it can be seen that the conditions for 0 rise and 0 pitch angle are identical. Furthermore, equation 47 explains that if the difference between the front suspension wheel rate and the rear suspension wheel rate is not large for the pitch angle to become 0, the height of the center of gravity must be lowered by nearly half under the condition of 0 rise, or the value of E over d must nearly double. In equation 47, if the front wheel rate is equal to the rear wheel rate, the condition for 0 pitch angle can be expressed as equation 48. Let's verify the above explanation with a figure. Let's look at the figure to see what geometry is needed to make the pitch angle 0. From the conditions expressed in equation 47 obtained previously, the geometry to make the pitch angle 0 can be expressed as shown here. In order to explain efficiently, I will explain using equation 48, assuming that the front wheel rate, Kf, and the rear wheel rate, Kr, are the same. In the figure, point U is a point located at twice the height of the center of gravity, Cg, and point S is the point where the horizontal line, parallel to the ground, passing through point U, intersects the vertical line, passing through the front tire contact center, A, on the road surface. To satisfy equation 48, the ratio of twice the height of the center of gravity to the wheelbase must be equal to the ratio of E to D. The line satisfying this condition can be represented by the blue straight line in the figure. The blue inclined line is the straight line connecting the rear tire contact center, B, and point S. If a virtual reaction point, SR, exists on the inclined line between point B and point S, then according to the property of triangle similarity, the ratio of 2h to L always has the same value as the ratio of E to D, thus satisfying equation 48. Therefore, if the virtual reaction point, SR, of the rear suspension exists anywhere on the blue straight line shown here, the vehicle can maintain a zero pitch angle during braking. As explained earlier, when rear wheel braking force is applied, in order to maintain a zero pitch angle, the rear ride height must decrease by the same amount as the front ride height decreases. Therefore, the final vehicle attitude with a zero pitch angle inevitably results in a decrease in both front and rear ride heights, ultimately becoming the attitude indicated by the black line. In a rear wheel braking vehicle, raising the virtual reaction point reduces the rear ride height. Let's briefly summarize the pitch geometry during rear wheel braking. It is important to note that, regardless of where the virtual reaction point is located, the amount of vertical dynamic load transferred from the rear wheels to the front wheels remains unchanged once the acceleration AX is determined. By the amount of the vertical dynamic load, the front ground reaction force increases and the rear ground reaction force decreases. Using the rise zero coordinate system explained earlier, the zero pitch angle condition can be expressed by equation 52, which represents the blue line. In the region below the blue line and above the green line, the pitch geometry can be expressed using an inequality as in equation 51. Similarly, in the region above the blue line, the pitch geometry can be expressed by inequality 53. If the virtual reaction point, SR, exists in the region between the green line and the road surface, indicated by yellow shading, the spring force, delta WZR, acts as a tensioning force on the spring, and the force on the suspension links, delta FZR, also acts as a tensioning force on the links. This direction is the direction in which the sprung mass rises. Ride height decreases at the front and increases at the rear compared to the steady state. If the virtual reaction point, SR, exists on the green line, the spring force, delta WZR, becomes zero, the rear spring displacement is zero, and delta FZR acts in the direction of tensioning the suspension links. In this case, the absolute magnitude of the force, delta FZR, is equal to the total vertical dynamic load of the vehicle. Since there is no change in rear ride height, this case is rise zero. Ride height remains unchanged at the rear and decreases at the front compared to the steady state. If the virtual reaction point, SR, exists in the area between the blue and green lines indicated by the blue shading, the spring force, delta WZR, acts as a compressive force on the spring, and in absolute terms, delta FZR tensions the suspension links with a force greater than delta WZR. Ride height decreases at both the front and rear compared to the steady state, but the decrease in ride height is greater at the front than at the rear. If the virtual reaction point, SR, exists on the blue line, the spring force, delta WZR, in absolute terms, becomes half the force of the suspension links and acts as a compressive force on the springs. This force is equal in magnitude to the vertical dynamic load transfer amount in terms of absolute value. Delta FZR acts in the direction of tensioning the suspension links. In this case, the force, delta FZR, becomes twice the absolute value of the vehicle's total vertical dynamic load. As the ride height decreases from the rear to the front level, the pitch angle becomes zero. If the virtual reaction point, SR, exists in the area above the blue line, the force compressing the links is greater than the force compressing the springs, and in absolute terms, the difference between these two forces is equal to the amount of vertical dynamic load transferred. Compared to the steady state, the rear ride height decreases more than the front ride height. If the virtual reaction point is located on the road surface, the height of the virtual reaction point is zero, so the link force is zero, and delta WZR acts as a tensioning force on the springs. In this case, the decrease in front ride height is equal in magnitude to the increase in rear ride height. If the virtual reaction point is located below the road surface, the height of the virtual reaction point is negative, and as shown in equation 54, delta FZR becomes positive, acting as a force that compresses the link. The force tensioning the spring is greater than the force compressing the link, and in absolute terms, the difference between these two forces is equal to the vertical dynamic load transfer amount. In this case, the increase in rear ride height is greater than the decrease in front ride height. In rear wheel braking, we should remember that if the braking deceleration is constant, the reduction in front ride height is constant, regardless of where the rear virtual reaction point is located. Let's find out the answer to the quiz. In a rear wheel braking vehicle, which statement is correct when the virtual reaction point is located between the rise zero line and the pitch angle zero line? First, in absolute values, the link force is larger than the spring force. Second, in absolute values, the link force and the spring force are not equal. Third, the rear ride height becomes smaller than in the static state. Fourth, the front ride height becomes smaller than in the static state. Fifth, the rear ride height is larger than the front ride height. Sixth, the rear ride height is larger than the front ride height. Therefore, the correct answer is number 6. The rear ride height is larger than the front ride height. Let me summarize the content of this video. I explained the pitch geometry of rear-wheel outboard braking vehicles. Rise is the phenomenon where the rear of a vehicle rises when braking with the rear wheels. Because the braking force generated horizontally at the tire contact surface acts below the center of gravity, the front of the vehicle body naturally lowers, while the rear rises. Anti-rise geometry refers to the geometric arrangement of the rear suspension links to prevent the rear of the vehicle from rising. I also explained the location of the virtual reaction point and vertical load transfer. Raising the virtual reaction point reduces the vertical dynamic load through the springs and increases the vertical dynamic load through the suspension links. Lowering the virtual reaction point increases the vertical dynamic load through the springs and decreases the vertical dynamic load through the suspension links. Rise and pitch angles were explained when rear braking force is applied. Zero rise means that the relative displacement of the rear spring is zero compared to the steady state, implying that the rear ride height has not changed. If the rise is zero, the rear spring displacement is zero, but the front spring displacement is not zero and decreases. The method for achieving a zero pitch angle was explained. To achieve a zero pitch angle, the rear ride height must be lowered to the level of the front ride height. To do this, the virtual reaction point must be raised. Raising the rear virtual reaction point increases the compressive force on the spring, thereby reducing the rear ride height. The method for achieving a zero pitch angle when the front and rear suspension wheel rates are equal was explained. Under the zero rise condition, the height of the center of gravity must be lowered by half, or the ratio of the vertical component to the horizontal component of the virtual reaction point must be doubled. The conditions for zero pitch angle were explained. As the front ride height decreases, the rear ride height must also decrease accordingly. Therefore, the front and rear ride heights must both decrease by the same amount. The physical principles regarding the position of the virtual reaction point in rear-wheel drive vehicles have been explained. If we use the tire road contact center under braking as a reference point, let SR be the ratio of the vertical distance to the horizontal distance of the virtual reaction point, and CR be the ratio of the height of the center of gravity to the wheelbase, then the change in ride height can be determined from these. If SR is less than 0, the rear increase is greater than the front decrease. If SR is 0, the magnitude of the rear increase and the front decrease are equal. If SR is greater than 0 and less than CR, the rear ride height increases and the front ride height decreases. If SR is equal to CR, the ride height remains unchanged at the rear but decreases at the front. In this case, the rise becomes 0. If SR is less than 2CR and greater than CR, the ride height decreases in both the front and rear, but the front decrease is greater. If SR is equal to 2CR, the ride height decreases by the same amount at the front and rear, and the pitch angle is 0. If SR is greater than 2CR, the ride height decreases in both the front and rear, but the rear decrease is greater. The relationship between the vehicle's total vertical dynamic load and the virtual reaction point has been explained. In rear-wheel braking, the vehicle's total vertical dynamic load is the amount of load transferred from the rear wheels to the front wheels. The amount of vertical dynamic load transferred is independent of the location of the virtual reaction point. The role of the virtual reaction point is to determine the ratio of load transfer transmitted through the springs and suspension links. Once the load transfer ratio is determined, the rise and pitch angles are determined. The rise and pitch angles can be adjusted using the location of the virtual reaction point. If you watch the previous videos, you can learn about various fields of vehicle dynamics and enjoy a more in-depth understanding of future videos. In a recent video, E0086, Pitch Geometry Part 6, the lift and pitch angles of a front-wheel drive vehicle with a front-independent suspension system were explained, and how the lift and pitch angles change depending on the 7 positions of the virtual reaction point. Additionally, it was explained that the front ride height can decrease depending on the position of the virtual reaction point, even during acceleration. In a recent video, E0087, Pitch Geometry Part 7, I explained the dive and pitch angles of a vehicle equipped with a front-wheel braking system, described how these angles change depending on the 7 positions of the virtual reaction point, and explained that even in braking, the front ride height can increase depending on the position of the virtual reaction point. The next video will be Pitch Geometry Part 9. I will explain the dive of a front-wheel braking vehicle equipped with an inboard braking system. If you found this video helpful, please hit the thumbs up and catch the brand new videos by free subscription. Also turn on alarms to be the first to see new videos. So, what are you waiting for? See you at next videos. Goodbye, guys.